this is Jimmy, and I'm going to talk about AI and autonomous driving systems, as well as some SLAM algorithm. And here's the agenda for today. As Tesla becomes one of the giants in autonomous driving industry, with its controversial CEO Elon Musk keeping making topics, ADAS along with the dedicated companies are coming into public's view. And it all started from 2004, the DARPA Grand Challenge, where each competing vehicles need to complete 132 miles course in desert terrain without human control. And fasting forward to today, many tech giants like Apple, Google, and Uber, along with Tesla, are heavily investing into autonomous driving systems, as well as some startup companies like Lyft and Apex.ai. Okay, so how does ADAS work? A typical ADAS system will consist of 4 parts, which are perception, estimation, prediction, and action. To be more specific, in perception section, the vehicle will use the sensors mounted on itself to obtain information from the environment and further process it. The estimation section will take those processed information from different sensors such as cameras, LiDAR, GPS, and fuse them to create a local map to help vehicle understand where itself at in this environment. Following that, the prediction section will use the history trajectory to predict the next movement of this vehicle and surrounding vehicle for action part to use. And the action part will take those informations and make higher level decisions such as path planning, collision avoidance, and emergency braking, etc. So in this system, the estimation and perception are usually looping with each other. It is like chicken and egg problem. By that I mean, in order to map the environment, the vehicle needs to understand its position. However, without precise map, it is usually hard for vehicle to position itself. This is the problem that the algorithm, simultaneous localization and mapping, or you can call it SLAM, is designed for. The flowchart in this page shows the working flow of one classical type of SLAM algorithm, which is landmark-based SLAM. Landmark SLAM basically means this SLAM algorithm only takes the landmark information from its environment, unlike the, for example, vision-based SLAM, where it takes pictures of the environment. And landmarks are usually some pole-like objects such as street light, traffic signal, that is labeled in a general purpose map. All the sensors are continuously harvesting the information such as the landmark, relative positions, distance from the odometry, and the raw positions from the GPS, and the preloaded general purpose map. All the information will be fed into either the local association or map association. Both of them combined together is called state estimation, or the sliding window sections down below in the red box. And those are for the results of the vehicle pose and landmark matching. Well, sounds complicated. Don't worry, let's break things down. Firstly, here's a picture describing the local association. As you can see, there is a vehicle traveling along the lane. The red stars could be some light poles on the side of the road. Since there's always errors in the reading of the sensors, the algorithm will make a cluster if the measurement of the landmark combined with the odometry readings are located within an acceptable range. With the clustering of the measuring readings, landmark reads from local associations are compared with the actual landmarks in the general purpose map. Once LAM finds a matching within acceptable error range, the map association is completed. These two steps, i.e. local association plus map association combined, is called state estimation. And the state estimation could be described mathematically. The top left equation shows the estimated state of the vehicle is chosen from the state and its maximum probability based on the measurements of landmark, odometry, GPS, and general purpose map. And it usually will be deducted into the quadratic form in the bottom left. And specifically for these landmark lengths, it could be further described in the equation on the right hand side. You recall from the page 6, there's a sliding windows plus sparse global area at the very bottom. This section is to optimize the performance of landmark SLAM. If you can look at the graph on the right hand side, the blue line means the measurements of the landmarks. To better position the vehicle, more landmarks measurements as well as the estimated poses are needed, which means the higher memory size and more computation per unit time is required. This could lead to catastrophic problem if the algorithm is not optimized. Therefore, the sliding window optimization is introduced. The graph on the top left shows how many steps of the state's vehicle will remember. As the picture shown here, you can see the matrix size means how many states of the vehicle along with the landmark detected are stored. For example, the red content in odometer reading from the step 0 to step 1 is stored at the second row and the first column in the matrix. Similarly, the map information of the first landmark denoted as 0 is stored at the 5th row and 5th column, since this is the information within the first landmark itself. Also, for the GPS signal in the blue, the landmark in the map is in yellow, and the landmark measurement in green are stored in the matrix accordingly. So in this slide, there are two videos showing how the algorithms is implemented in both the simulation and the real world. The first video on the left hand side shows the visualization of the simulation. As you can see, the reading of the odometer in the purple line is not very accurate. On the right hand side is the realization of the landmark SLAMs on the Arduino robots in the real world. So that's pretty much it for today's presentation of mine. I hope you're enjoying these two topics and actually learn something from my presentation today. Thank you again for your attention. Wish you have a nice day.